I'm going to talk about improved Merlin-Arthur protocols for central problems in fine-grained complexity. This is a joint work with Shyan Akmal, Lijie Chen, Malvika Raj, and Ryan Williams. I'm Jing. So let me start by explaining the two keywords in the title, Merlin-Arthur protocols and fine-grained complexity. Suppose we have two parties, Arthur and Merlin. Suppose Arthur wants to evaluate a certain function, but he only has very limited computational power. So he lets Merlin help him compute the answer. To prevent him from cheating, he also wants Merlin to prove to him that the answer is correct. To do this, we let Merlin sends the answer y together with a proof string z of length p of n to Arthur. Then Arthur runs a randomized verification procedure which runs in t of n time on a word RAM machine. Then we let this protocol to satisfy two properties. The first is completeness. If the answer is correct, then there exists a proof such that the verifier accepts with probability 1. And the soundness requirement is if the answer is incorrect, then for all proof strings, the verifier should reject with probability at least 2/3. We say the Merlin-Arthur time of this protocol is the proof length plus the verification time. Meaning that we take into account the time for reading the entire proof string. And here we remark that if we require the rejection probability to be 1, then this protocol becomes a non-deterministic algorithm. Now let's look at fine-grained complexity. In fine-grained complexity, there are several central problems which are conjectured to be hard, such as threesome, orthogonal vectors, and all pairs shortest path. And based on these hardness assumptions, we can use fine-grained reductions to show conditional hardness of many other problems. And recently, there is some interest in studying Merlin-Arthur protocols for central problems in fine-grained complexity. For example, let's look at the previous work of Williams, which gave a Merlin-Arthur protocol for the orthogonal vectors problem, which is a central problem in fine-grained complexity. Here we are given two lists of 0, 1 vectors, and we want to decide if there is a pair of orthogonal vectors. And the best known algorithms for this OV problem needs roughly quadratic time, and this is conjectured to be near optimal. Williams in 2016 gave a Merlin-Arthur protocol for counting the number of orthogonal vector pairs, and the running time of this protocol is roughly n times d, where d is the dimension of the vectors. So this running time is near linear in the input size, so it's near optimal. And it achieves a nearly quadratic speed up compared to the best known algorithm. And this result refuted the Merlin-Arthur strong exponential time hypothesis. And the algebraic techniques used in Williams' results have been applied in many subsequent works. For example, the Berkeley and Kasky's protocols for many other problems, and a sequence of results on fine-grained cryptography and average case fine-grained complexity. And here we consider the following question. Can we get fast Merlin-Arthur protocols for other problems in fine-grained complexity? And in this paper, we showed the answer is yes. We can obtain near optimal MA protocols for threesome and APSP, which are two other central problems in fine-grained complexity. And we also have many more additional results. So our new results in this paper can be divided into 4 groups. Now let's introduce each of them. Our first set of results is about the KSum problem, where we are given n integers and we want to decide if there exists k of them that sum to 0. The best known algorithm for threesome runs in roughly quadratic time, and it's conjectured to be optimal. More generally, for KSum, the best known running time is n to the ceiling of k over 2. In this paper, we show that certifying that no KSum solution exists can be done in Merlin-Arthur time roughly n to the k over 3, ignoring polylog n factors. So in particular, no threesome can be certified in near linear MA time. We can compare this with the previous results by Carmosino et al., which showed that no threesome can be certified in n to the 1.5 non-deterministic time. So our results achieved a better running time by using the power of randomness in the protocol. Our threesome protocol also has several implications for many other problems. So let's look at the subset sum problem, where we are given n integers and a target t. We want to decide if there exists a subset of them that sums to t. The best known algorithm for this problem runs in 2 to the n over 2 time. And by a simple reduction from subset sum to threesome, our protocol implies that no subset sum can be certified in roughly 2 to the n over 3 MA time. This improves the previous result by Nederlof, which showed a protocol in 2 to the 0.49991 n MA time. We also considered the closely related mean plus convolution problem. This problem is also conjectured to require n squared time. And using the techniques from Vasilevska and Williams, our protocol implies the following. The mean plus convolution problem can be computed in near linear MA time. Now let's look at our second set of results, which is about counting cliques. Previously, there are several results on Merlin-Arthur protocols for counting k cliques in an n-vertex graph, and they achieved nearly quadratic speedup compared to the best known algorithms. And here we study a harder problem, which is counting zero-weight k clique. Here, the input graph has integer edge weights, and we want to count the number of k cliques with 0 total weight. The best known algorithm for this problem roughly takes n to the k time. And here we show that this problem can be solved in MA time n to the ceiling of k over 2. So this is a quadratic speedup for even k. In particular, when k equals 4, we can solve the counting zero-weight 4-clique problem in MA time n squared, which is near optimal for dense graphs. And we also have improvement for odd k on sparse graphs. For example, when k equals 3, we can solve counting zero-weight triangle problem by a MA protocol with verification time near linear in the number of edges and the proof length near linear in the number of vertices. Our zero triangle protocol has implications for the APSP problem, where we are given a directed graph on n nodes and we want to compute the shortest distance between every pair of nodes. Our protocol implies that the APSP problem can be solved in nearly n squared MA time, which is near optimal. We can also compare this with the previous result by Carmosino et al., which showed that APSP had a n to the 2.94 non-deterministic algorithm. Again, our protocol achieves a better running time by using the power of randomness. Our third result is about KOnset. Suppose we're given a KCNF. The brute force algorithm for deciding whether this KCNF is satisfiable or not runs in roughly 2 to the n time. But there are faster algorithms which achieve an improvement of a constant times n over k on the exponent. Here we are ignoring factors that are polynomial in the input size. And in this paper, we show that certifying that the KCNF is unsatisfiable can be done by a Merlin-Arthur protocol in roughly 2 to the n over 2 minus a constant times n over k time. Previously, the fastest Merlin-Arthur protocol for KOnset by Williams needs a larger running time, 2 to the n over 2. And this protocol actually solves a harder problem of counting the number of satisfiable assignments. And here we remark that Williams' protocol algebraizes in the sense of Aronson and Wiglerson. And we can show that there is no algebraizing protocol for KOnset in faster than 2 to the n over 2 time. So in our protocol, we have to exploit non-algebraizing properties in order to obtain our improvement. Our fourth result is about quantified Boolean formula, where we are given a quantified Boolean formula in pre-next normal form, and we want to decide whether it is a true QBF. So this is a canonical p-space complete problem with a trivial algorithm that roughly takes 2 to the n time. Previously, Williams gave a 3-round Arthur Merlin-Arthur protocol, which runs in 2 to the 2n over 3 time. Here, the proof by Merlin depends on the randomness of Arthur in the first round. And Williams asked the open question of whether there is a Merlin-Arthur protocol that achieves a non-trivial running time. And here we affirmatively answer this question by showing a Merlin-Arthur protocol for a true QBF in 2 to the 4n over 5 time. So these are all the new results in our paper. For the rest of the talk, I'm going to describe our near linear time MA protocol for the threesome problem. Let's first recall the definition. We are given input integers a1 through an, and a threesome solution is a tuple of 3 indices ijk, such that ai plus aj plus ak equals 0. Here, for simplicity, we allow repeated indices among ijk. And our task is to certify that no threesome solution exists in our input integers. And we want to do this in near linear MA time. So our first step is to reduce the no threesome problem to a counting threesome problem with small input range. And here we are going to use the idea from the previous work of Carmosino et al. Let's pick a positive integer d, and let's define a relaxed threesome solution to be a tuple of ijk such that ai plus aj plus ak is equal to 0 mod d. So a solution must also be a relaxed solution, but a relaxed solution may not be a real solution. And because there are n cubed tuples in total, we can show that there exists a integer d that is less or equal to n squared, such that there are at most O tilde n relaxed solution. Here we are ignoring log factors. Now, in the protocol, the prover sends this integer d to the verifier, and he also sends the list of all the relaxed solution to the verifier. And here, let's use m to denote the length of this list of relaxed solutions. Then the verifier wants to verify 3 statements. First, the 3 tuples in this list are distinct, and they are all relaxed solutions. Second, none of these relaxed solutions are real threesome solutions. Third, he wants to verify that the input has exactly m relaxed solution, where m is the length of this received list. If all these 3 statements are true, then the verifier is convinced that there are no real threesome solutions in the input. The first 2 statements are easy to check, so it remains to verify the third one, which is a counting problem. Since now we only care about relaxed solutions, namely the threesomes that are equal to 0 mod d, we can reduce all the input integers mod d. So our new task is we are given n input integers that are from 1 to d, where d is less or equal to n squared. And we want to prove that the number of tuples that sums to t is exactly m sub t. And here, we'll repeat this for every target t from the possible multiples of d, which are d, 2d, and 3d. And we want to prove the solution count for each of them. And we want to check that they sum up to m. Okay, so in order to solve this counting problem, we are going to consider the generating function of the input instance. Let's define a polynomial a of x to be the sum of x to the ai for all input integers ai. And we have assumed that ai is at most n squared, so this polynomial has degree n squared. And we consider a of x cubed, and we use b sub j to denote the coefficient of this cubed polynomial. And we can easily see that the number of tuples summing to t is exactly the tth coefficient, b sub t. And now we are going to use a technique that is inspired by the previous work of Nederlof. Let's define a set of numbers, capital T, which is a arithmetic progression of common difference n, and it includes t, and it also includes all the numbers that are equal to t mod n. So we can see that capital T has at most 3n squared over n numbers, which is linear in n. And now Merlin not only sends his solution count m sub t, but also the m sub j for all the elements j in capital T. And Merlin claims that they are equal to the correct jth coefficient in a of x cubed. namely that he claims M sub j equals to B sub j for all j in capital T. And Arthur wants to check whether his claim is correct. So he picks a random element R from a large enough finite field and checks the following equality. Here, the left-hand side is a polynomial in R, and the coefficients are given by Merlin. And on the right-hand side, this is the corresponding polynomial with the actual coefficient B sub j. And by Schwarz-Zippel lemma, if the claim is false, then Arthur can catch it with a very good probability. And in order to check this equality, he needs to evaluate both sides. The left-hand side is easy to evaluate. So the problem is how to evaluate the right-hand side. Here, let's observe that if we consider a of r times x cubed, then this is going to multiply an extra r to the j factor to every term in this polynomial. Now, if we mod x to the m minus 1, then we can reduce the exponent on x from j to j mod n, which means that we merge all the terms that have the same x exponent mod n. And recall that the expression we want to evaluate is the sum of bj times r to the j for all the j in capital T, namely the j that are equal to T mod n. So we can immediately see that this expression equals the x to the T mod n term coefficient of this expression. So all we need to do is to evaluate this. And to evaluate this, we can first reduce the a of rx mod x to the m minus 1, which can be done in linear time. And then we raise it to the third power, which can also be done in linear time using FFT. So the total MA time of this protocol is the proof length, which is roughly the size of capital T, plus the verification time, which is also linear in n. So the total MA time is linear in n. Now let me mention several open problems. First, can we certify no subset sum in 2 to the n over 4 MA time? In this paper, we achieved 2 to the n over 3. Second, can we certify true QBF in 2 to the n over 2 MA time? In this paper, we only achieved 2 to the 4n over 5. Thanks for listening.